Children, in this video we are going to learn about Rauolts law. Before that, a general fact regarding vapor pressure of liquid, that is, consider a liquid in a vessel. Generally, the liquids have a tendency to evaporate. Everybody know. But if you are keeping some water in a beaker also, it is continuously, it gets evaporated. So, if the kinetic energy of molecule in the liquid state, if it overcomes the intermolecular force of attraction between them, then the molecules will escape from the liquid state. This process is called as evaporation. This process is called as evaporation, as it happens on the surface of the liquid. If this evaporation, when carried out in a closed container if it is closed, in a closed container, then the vapor remains in contact with the surface of the liquid. These vapor molecules are in continuous random motion during which they collide with each other and with the walls of the container. Since the collision is inelastic, they lose their energy, and as a result the vapor returns back to liquid state. That process is called as condensation, in which the vapor returns back to liquid state. So evaporation, condensation, they are the continuous process. If the process carried out in a closed system, a stage is reached when the rate of evaporation becomes equal to the rate of condensation. Thus, an equilibrium established between the liquid and vapor. Liquid and vapor. So, the pressure of the vapor in equilibrium with its liquid, that is called vapor pressure of the liquid. Vapor pressure of the liquid at the given temperature. So the vapor pressure of a liquid depends on its nature, temperature and surface area. So in a book, a simple diagram given to represent the vapor pressure of a liquid. See, consider this diagram. This is a round bottomed flask. This is the round bottomed flask. Here ethanol is kept, and this is the U-tube carrying mercury. Now this container is closed, so the ethanol is in equilibrium with its vapor as per this apparatus. Now see this apparatus, here also ethanol, and this is the vapor. Now the vapor, now here it is closed. This container, it is closed. So vapor remains here itself. Now this container is opened. So what happens? See, this vapor comes out and pushes the level of the mercury to the upper. So the difference in the mercury level, see, the difference, this gives the vapor pressure of ethanol present in the round bottomed flask. So this is the vapor pressure of the liquid. Since it pushes the mercury level, this shows the vapor pressure of the liquid, that is ethanol, in the round bottomed flask. So the vapor pressure when a solute is dissolved in a liquid solvent, when a solute dissolved in liquid solvent, that is called liquid solution. The solution which contains only two components, that is one solute and one solvent, that is called a binary solution. So now let us consider a binary liquid solution followed by dissolving a liquid solute A in a pure solvent B in a closed vessel. Both the components A and B present in the solution would evaporate and an equilibrium will be established between the liquid and vapor phase of the components A and B. So the French chemist Rauolts proposed a relationship between partial pressures and mole fractions of the two components A and B, which is known as Rauolts law. Based upon this slide states that in the case of a solution of volatile liquids, volatile means easily evaporating, the partial vapor pressure of each component A and B, why partial? Because shared between the both, is directly proportional to the mole fraction. So now consider partial pressure of A directly proportional to mole fraction of A. Equation 1. So partial pressure of A by removing the proportionality sign, a constant K into XA, mole fraction of A. When XA is equal to 1, K XA, that is mole fraction of A is equal to 1, proportionality constant K is equal to P naught A, that is vapor pressure of the pure component. P naught A is vapor pressure of the pure component. Substitute here. So therefore PA equal to P naught A, because K value is P naught A, into XA. This is equation 2. PA is equal to P naught A into XA, equation 2. Similarly, for component B, PB equal to P naught B into XB. This is the equation 3, where XB and XA are the mole fraction of the components A and B respectively. According to Dalton's law of partial pressures, the total pressure in the closed vessel will be equal to the sum of the partial pressure of the individual components. Hence, P total is equal to PA plus PB. So, substitute PA means P naught A into XA plus PB means P naught B into XB. This is equation 4. We know that XA, mole fraction of A plus mole fraction of B is equal to 1, or mole fraction of A is equal to 1 minus mole fraction of B. So therefore P total equal to 1 minus XB into P naught A plus XB into P naught B. P naught B. So upon expanding, lastly we are getting P total equals to P naught A plus XB into P naught B minus P naught A. The above equation, this equation is of the straight line equation form, y is equal to mx plus c. The plot of P total versus XA will give a straight line with a slope as P naught B minus P naught A and P naught A as the y-intercept. Now let us consider a liquid solution containing toluene and benzene. Toluene and benzene. Toluene is the solute, benzene is the solvent. Both are in liquid state. So now by plotting the graph, vapor pressure, here mole fraction of benzene and mole fraction of the solvent. For benzene, the pressure is 74.7 millimeter of mercury. For benzene, it is 22.3. By combining the both, we are getting a straight line. This line is given clearly in your book. This line shows that the partial pressure of the pure components increases linearly with increase in the mole fraction of the respective components. So, in the case of a binary solution of solid in liquid, but in the case of binary solutions of solid in liquid, what happens? Solid in liquid. When a non-volatile solute, non-volatile means cannot easily evaporate. When a non-volatile solute dissolved in a pure solvent, the vapor pressure of the pure solvent will decrease. So in each solution, the vapor pressure of the solution will depend only on the solvent molecule as the solute is non-volatile. For example, when sodium chloride added to the water, it is given clearly in your book. When sodium chloride added to the water, the vapor pressure of the salt solution is lowered because it is determined by the number of molecules of the solvent present in the surface at any time, and it is proportional to the mole fraction of the solvent. So it is considered that pressure of a solution directly proportional to mole fraction of A, where Xa is the mole fraction of the solvent. So pressure of the solution is equal to K into Xa. When Xa is equal to 1, K is equal to P naught solvent. So pressure of the solution is equal to P naught solvent into Xa. So pressure of the solution by P naught of solvent, that is vapor pressure of solvent, is equal to Xa. That is 1 minus pressure of the solution by vapor pressure of the solvent is equal to 1 minus Xa. That is pressure of the solvent minus pressure of the solution by vapor pressure of the solvent is equal to Xb, where Xb is the mole fraction of the solute. The above expression gives relative lowering of vapor pressure. Based on this expression, Rauolts' law also can be stated as relative lowering of vapor pressure of an ideal solution containing non-volatile solute is equal to the mole fraction of the solute at a given temperature. So according to Rauolts' law, pressure of the solute is equal to vapor pressure of the solute into mole fraction of the solute. But according to Henry's law, pressure of the solute is equal to constant into mole fraction of the solute. So the difference between the above two expression is the proportionality constant P naught A, which is for Rauolts' law, and KH for Henry's law. Henry's law is applicable to solution containing gaseous solute in liquid solvent, while Rauolts' law applicable to non-volatile solid solute in a liquid solvent. If the solute is non-volatile, then the Henry's law constant will become equal to the vapor pressure of the pure solvent, and thus Rauolts' law becomes a special case for Henry's law. So for very dilute solution, solvent obeys Rauolts' law and the solute obeys Henry's law. Solvent obeys Rauolts' law, solute obeys Henry's law.